In this video, we will learn about the time complexity of algorithms, aka the Big O notation. You will learn what is the Big O notation, why do we use it, and how it can help us write clean, efficient, and scalable code. So, starting with what is the Big O notation, we can define it as how the code slows as the input size grows. Or, in other words, we study the performance of an algorithm with respect to the increasing input size. One thing to note here is when we talk about the time complexity of an algorithm, it means the number of steps the algorithm takes to finish and not its overall execution time. This is because the execution time of an algorithm can be affected by various factors such as the hardware component running the code and the programming language. When measuring the time complexity of an algorithm, we tend to ignore any smaller numbers and only worry about the worst case scenarios. For example, big O of n plus 1 will always be treated as big O of n because anything added to the n will eventually becomes n. Now let's take a look at the first example. Before we start off, I'm going to create three different kind of variables. The first one is just creating a simple linearly spaced vector that contains 10,000 elements. The next one is the jumbled version of that vector, and the third one is of course the negative vector. So we will start off with our first example, which is the constant time algorithm. Suppose we have an array of elements and we want to access a specific value by its index. As you can see here, the algorithm is executed in a single step, and no matter how large the input size gets, time complexity will always be equal to big O of 1 or constant time. We can verify that in this figure. Now let's move on to another example. Suppose we have a sorted array of n number of elements and we want to find a specific target value inside that array. I'm going to implement a simple binary search algorithm here. We will initialize our first and last pointer and iterate over the array by finding the middle value and comparing it with the target. At each iteration, the search space is reduced by half, which means as the input size grows, the algorithm gets much more efficient. The time complexity of this algorithm is big O of log n. As you can see here in this figure, as the input size grows, the algorithm becomes much more efficient. Now, suppose we want to search a specific target element in an array by searching it sequentially, the time complexity will grow linearly with the input size. Because in the worst case scenarios, we'll have to check every element once and perform n number of comparisons. As you can see in this figure, time complexity grows linearly with the passage of time and input size. For the next example, let's assume that we have a jumbled list that we want to sort. I will use the divide and conquer rule for this job, and we'll implement a merge sort function. This function has two parts, the divide and the conquer. The divide part takes a list of input elements and check for the base case first. If the size of the array is less than 1, it means that there's nothing to sort and the function breaks. But if the base case isn't satisfied, we move forward and check for the middle value. Then using the middle value, we will divide the list in two halves and we'll call it the left and the right half. Now when we pass the output to the conquer function, here we will iterate over both halves, compare their values, and append. Once the loop finishes, we will get a final sorted list. Since the merge sort algorithm divides the list in half log to the base 2 of n times, at each level we do a merge which touches n number of elements performing big O of n work per level. So the time and complexity of this algorithm is big O of n log n. Now let's discuss another sorting algorithm. This time we will implement a simple function called bubble sort. Inside this function, I will simply find the length of the input list and then run two for loops in nested setting. I'm simply comparing the element at the jth index with the next element and swapping their position. Once the loop finishes, we will get a sorted list. Since we are using nested for loop here, therefore the time complexity of our algorithm will grow quadratically. Finally, let's discuss one last algorithm where we will find zero-sum triplets. Here, I'm using 3 for loops in a nested settings to find all the combination of negative numbers whose sum is equal to 0. Since we are running 3 for loops, therefore our time complexity will grow cube times. And that's it. Before ending this video, let me give you a quick comparison of all the time complexities. The most efficient one is the constant time complexity. As you can see here, as the input size grows, the time complexity remains constant. The next one is the logarithmic time complexity, which means as the input size grows, the algorithm gets more efficient. Then we have the linear time complexity, and as we can see from this figure, it performs best for the smaller inputs, but as the input size increases, the performance reduces. The quasi-linear may perform very good for the smaller inputs, but when the input size increases, it gets much worse. And finally, the rest of the two are pretty much self-explanatory. So that's it, guys.